If this machine makes a mistake of just 1 millimeter, the round it's building could explode and blow up the building. In this factory, close enough isn't an option. But they don't just need to make one perfect round. They need to make 1 million of them, every single day. We've been given full access to see the chemistry, the robotics, and the ballistics testing inside a modern bullet factory. This is the most dangerous assembly line on Earth. Welcome inside. Every round starts as a flat strip of yellow metal. This is 70/30ths cartridge brass, 70% copper, 30% zinc. We don't use steel, and we don't use aluminum. We use brass because of a phenomenon called obturation. When 60,000 psi of pressure detonates next to your face, this metal becomes a gasket. It expands to seal the dangerous gases, then instantly shrinks so you can extract it. And the process begins with violence. This is the blanking press. It punches out these little discs, called cups, at a rate of thousands per hour. This is the ancestor of the bullet case. But right now, it's useless. It's short, fat, and hard. To hold gunpowder, we need to turn this into a long, thin tube. This brings us to the draw. We are going to force this metal to flow like a liquid. A tungsten carbide punch smashes into the cup, forcing it through a die slightly smaller than itself. It elongates the metal, but here is the engineering trap. As you stretch brass, you stress it. It becomes brittle. If we tried to stretch this again right now, it wouldn't bend. It would shatter like glass. So, we have to reset the metal's memory. This is annealing. By heating the cups to 1,100 degrees Fahrenheit, we reset the crystal structure. We make the metal soft again so we can torture it some more. They repeat this cycle 3 or 4 times. Stretch, heat, until that squat little coin has transformed into a perfect tall cylinder. We have the height, but look at that top edge. It's jagged, it's uneven, and right. Now, it can't hold a bullet. That is about to change. The hardness paradox. We frame the final annealing not just as a step, but as a solution to an engineering contradiction. Needs to be hard and soft. We left off with a jagged, uneven tube. The first step to fixing it is surgical. The trim machine slices the case to a microscopic tolerance. Now, the case needs a handle. This is the header press. In a single, violent impact, it crushes the bottom of the tube flat to create the rim and the primer pocket. This rim is the only thing your gun has to grab onto. When you fire, the extractor hook latches onto this piece of brass to rip the empty shell out. If this rim is too weak, it snaps off. The gun jams, and in a firefight, that is a catastrophe. Simultaneously, a tiny pin pierces the center of the pocket. This is the flash hole. It's the ignition tunnel. Without this hole, the spark from the primer can't reach the gunpowder. It's a tiny detail, but precision is everything. If this hole is off-center by a fraction of a millimeter, the firing pin hits dead metal. The round is a dud. Now, if this were a pistol round, we'd be done. But this is a rifle round. We need to turn this straight pipe into a rocket nozzle. The case is forced into a tapered die that squeezes the neck down. This shape allows us to pack a massive volume of slow-burning powder behind a small, aerodynamic bullet. It essentially pressurizes the gas to send the projectile supersonic. You've probably seen military ammo with this purple stain around the neck. People think it's heat damage. It's actually proof of quality. This is the final anneal, and it creates an engineering paradox. We need the bottom of the case to be incredibly hard so it doesn't blow out under 60,000 psi. But we need the neck to be soft. Why? So it can expand to release the bullet, seal the gas, and then spring back. If the neck was as hard as the base, it would split open the moment you pulled the trigger. The brass is polished, measured, and structurally perfect. It is a precision-engineered musical instrument, but right now, it has no sound. To make it sing, we need to head to the other side of the factory. We need the projectile. While the brass line is ringing like a bell, the other side of the factory is silent and heavy. This is the lead room. Most people think bullets are cast, melted, and poured into molds like toy soldiers. In a modern factory, that is way too slow. Here, they don't melt the metal, they crush it, This is cold swaging. High-speed cutters chop this wire into precise little nuggets called cores. But there is a problem. Lead is soft. If you fire raw lead at 3,000 feet per second, the friction is so intense it would literally melt the surface of the bullet and foul up your barrel. To survive the trip, the lead needs armor. That armor is copper. This is the jacket. This is the marriage. A hydraulic ram forces the soft lead core inside the hard copper cup. Now, we have a projectile that is heavy enough to carry energy, but tough enough to engage the rifling without melting. But it's still shaped like a soup can. It needs to be aerodynamic. The ogive die crushes the nose into that perfect geometric curve. For high-precision, long-range rounds, they also taper the back end. This is a boat tail. It reduces the drag of the air trailing behind the bullet, keeping it stable at supersonic speeds. See the serrated groove? That's the cannelure. It acts as a lock. When a machine gun fires, the recoil is violent. Without this groove for the brass to crimp onto, the bullet would be pushed back inside the case. That reduces case volume, spikes pressure, and blows up the gun. Consistency is king. Lasers and scales check every single projectile. A grain is 1/7,000th of a pound. If a bullet is off by a fraction of a grain, it's trash. We have the car, the projectile, and the garage, the case. But right now, it's just a paperweight. To turn it into ammo, we need the fuel. And this is where things get dangerous. Changes made for high stakes and context. The static threat. We visualize the invisible threat of static electricity immediately to heighten tension. Primary versus secondary explosive. We clarify the chemical difference between the primer, sensitive, and powder, stable but powerful, to explain the different handling procedures. The geometry of fire. We focus on the shape of the powder granules as an engineering marvel, rather than just it's not dust. The rules change here. We are entering the loading zone. In this room, a spark from your sweater could level the building. I have to discharge all static electricity before entering. The floor is conductive to keep us grounded. The humidity is pumped up to suppress sparks. Why? Because of this. This is the primer. It contains a chemical mix, often lead stiffenate, that is impact sensitive. It doesn't need fire to explode, it just needs to be hit. That machine is pressing the primer into the brass pocket we made earlier. It has to be gentle. If the machine pushes too fast, or if a piece of grit gets in the way, bang. You have a detonation on the line. That's why this happens behind blast shields. Sensors monitor the force of every insertion. If a primer is upside down, the machine kills the power instantly. Once the spark is seated, we need the fuel. Modern smokeless powder isn't a fine dust like in the movies. It's precision extruded geometry. See these tiny sticks? Their surface area controls the burn rate. Left fine powder burns, instantly pressure spike barrel explodes. Right extruded sticks burn progressively smooth pressure curve bullet accelerates safely. This is the difference between a push and a bomb. If the powder burns too fast, the pressure spikes before the bullet moves, blowing up the gun. If it burns too slow, the bullet leaves the barrel at half speed. It has to be chemically timed to the millisecond. A volumetric dispenser drops a precise charge into every case. But machines can clog, and a clogged nozzle is a disaster. This is the most critical safety check in the entire factory. Immediately after the drop, this rod dips into the case to physically measure the height of the powder. Scenario A, rod goes too deep, no powder. Result, squib load, bullet stuck in barrel. Scenario B, rod hits high, double charge. Result, catastrophic failure, gun explodes. If there's too much, a double charge, the gun explodes. If there's too little, a squib. The bullet gets stuck in the barrel, and the next shot blows the gun up. If this sensor trips, the entire assembly line freezes. Green light, the charge is good. Now we have a primed, powder-filled grenade with an open top. We need to cap it off. We are in the home stretch. The case is primed, the powder is volatile, the bullet is ready. It's time to seal the deal. The seating die pushes the projectile down into the neck. But it doesn't just push it in, it pushes it to a specific depth measured in thousandths of an inch. This is the coal, cartridge overall length. This is a Goldilocks game with lethal consequences. If the bullet sits too high, it will jam into the barrel's rifling, and the gun won't close. But if it sits too deep, you reduce the volume inside the case. Less room means higher pressure. It turns the chamber into a pipe bomb. The bullet is seated, but it's not secure. If you drop this round now, the bullet might slide. We need to lock it. This is the crimp. Remember that serrated cannoneer groove on the bullet? The crimping die squeezes the lip of the brass neck directly into that groove. This ensures that the violent recoil of a machine gun, or just dropping the ammo box on the concrete, push the bullet back into the casing. It is physically locked to the brass. And just like that, what was once a pile of dull wire and dangerous chemicals is now a precision-engineered product. But they aren't allowed to leave yet. Before these rounds can be shipped to the front lines or the store shelves, they have to pass the final exam. And this exam is graded by a laser. In the old days, quality control was done by the human eye, but the human eye blinks in 100 milliseconds. In that time, this machine has already inspected 5 rounds. This is 100% automated inspection. Every single round that leaves this line runs through a 360-degree laser scanner. It's checking dimensions to the micron. It checks case length, neck diameter, and crucially, primer depth. If a primer sits too high, the gun's bolt could slam it and fire the round before the chamber is closed. That is a catastrophic failure. The laser catches that before it happens. But lasers can only measure shape. They can't measure power. For that, you have to shoot. This is the ballistics tunnel. Every lot, a batch of roughly 50,000 rounds, is sampled here. This isn't a normal rifle, it's a universal receiver. It's bolted down to remove human error. They aren't just checking to see if it goes bang, they are measuring the physics of the explosion. They measure velocity using chronographs. But more importantly, they measure pressure using piezoelectric sensors drilled directly into the barrel. They need to see a consistent pressure curve. If the pressure is too low, the bullet is slow. If it spikes too high, it's dangerous. And finally, accuracy. If this sample group spreads out too much, or if the pressure deviation is too high, do you know what happens to the 50,000 rounds sitting on the pallet outside? They are scrapped, all of them. It cost the company thousands of dollars to destroy this batch. But in this industry, a recall isn't just a refund. It's a matter of life and death. The survivors, the rounds that passed the laser and the ballistics lab, hit the victory lap. These are Delta robots. They orient the rounds and slide them into plastic trays faster than the human eye can track. From trays to boxes, from boxes to cases, from cases to pallets. And here is where physics comes back to bite you. Lead is one of the densest materials on Earth. This single pallet is barely waist high, but it weighs over 2,000 pounds. It's like parking a Honda Civic on a wooden skid. Shipping this is a logistical nightmare. Every truck is a rolling magazine. They need specific placards, specific routes, and specific licenses. But every day, millions of rounds leave this facility, heading to police departments, military bases, and sporting goods stores around the globe. It's easy to look at a bullet and see a simple, disposable object. Just a piece of metal you throw away at high speed. But as we've seen, this is actually a vessel of pressure, chemistry, and extreme tolerance engineering. To make one of these by hand, measuring every grain of powder, takes a skilled craftsman 10 minutes. To make 1 million of them a day, with the exact same precision, takes a symphony of automation. Thanks for coming inside the factory with us. We just showed you how to mass produce a supersonic projectile. But if you want to see the ultimate challenge in manufacturing, you need to click this video right here. We are going inside a jet engine factory. A bullet has 4 components. A jet engine has 30,000. We're talking about blades that spin at 10,000 revolutions per minute and temperatures hot enough to melt the metal they are made of.